welcome back to JAX London 2020 Online. My name is Maika Möbus, and I'm here with Richard Warburton and Sadiq Jaffer from Opsian. Hi, Richard and Sadiq.
Hi.
Hello.
So, as always, we have a chat function in Swapcard, and you can also ask questions. And Richard and Sadiq will get to your questions at the end of the talk. And now, please enjoy the talk called No Free Lunch, Memory Allocation in the JVM.
Great. Hi, I'm just going to do a bit of screen sharing. You see me all right there?
Yep.
Good. Hi. So as we've just introduced, I'll skip that. This is a talk. I'll reintroduce myself. I'm Sadiq, and this is Richard. We're from Opsian. We're a performance tooling consultancy company. There should be some joke here that this is a virtual conference, and so in fact none of you have had a free lunch, and thus it is very relevant to our talk. But it is sad there's no free lunch, basically. This talk is going to be about memory allocation in the JVM, how it works, why it's not free, why it's hard to reason about, and then what tools we can use to better understand it.
So I'm sure there are lots of people out there thinking, you know, look, I know how to understand code. I've got an IDE. It works great. I'll just read the code in that. But actually, in this talk, we are going to share the #1 way software engineers can improve their performance optimization skills. It's very simple, and yet something so few of our fellow engineers do, and it will really help them. That is to stop before you jump into reading your code directly. It's great to read the code, but what we want to do is take a more scientific approach here, grounded in measurement and testing, and actually understanding what the code is doing in production, rather than reading the code on screen and theorizing about it. So there's a few different topics in this talk. Firstly, we're going to talk about what allocation actually is. Then we're going to look about how it works, so a little bit of the theory of how JVMs work under the hood. And then looking about how you reason about memory and the tooling to understand it as well. Okay, but first, let's dive into precisely what allocation actually is. Well, certainly for the purpose of this talk, we're thinking about allocation in terms of creating a new Java JVM object. So inside the JVM, there's a space of memory called the heap space, and we want to reserve within the heap memory for an object, the value of the object to be written into. So most of the time, that will resolve around the new keyword in Java being called and an object being allocated. It's worth noting that primitive values don't entail object allocation. So a local variable that's a primitive will live on the stack, and the value of a local variable that's in a field will live within its parent object's heap space. But the new keyword isn't the only way that objects get allocated in the JVM. There's also things like string concatenation as well. And bear in mind that if you call another method, that might also new up an object as well. So in practice, most of the allocation in your system probably won't look in code like the new keyword is there. But we'll look at more on that topic a bit later.
Great. So we've defined what allocation is, and now we're going to look at how the JVM actually goes about doing allocation. Now, the JVM's memory system is huge, right? It spans, it's a big topic, and we're only going to be looking at just the very beginning, right? Just how allocation works, not about the rest of the GC machinery and memory subsystem of the JVM. So how does allocation itself work? Well, in Java, Java uses something called pointer bumping. Now, the way pointer bumping works is we have a fixed region in which we want to allocate in. We have a pointer to our current position in that region. And then when we want to actually do an allocation, what we do is we bump the pointer by some amount, where that some amount is the size of the object we want to allocate. And in Java, the size of the object we want to allocate is the size of the object header, and then the size of the fields that are in that object. So we bump it by that amount, and then we check is that new amount that we've got, is that over the end of this allocation region? And if it isn't, great, we can basically use that space we've reserved to, and we can populate the fields and start initializing that object, right? And that's the path that nearly all object allocations will go through in the JVM. There is a separate path for objects deemed large by the GC, and that goes through a kind of a different, potentially slower path because they're less frequent in their occurrence. Now, it's worth contrasting pointer bumping with an alternative that's used quite heavily in malloc implementations that you might find in C or C++. And that is having free lists, where when you want to allocate, you search these data structures for a particular size space that this object will fit into, and then you basically use that space. So that requires a bit more complex looking around multiple places for somewhere the object could go. In contrast to that, pointer bumping is literally adding something to a pointer and doing a comparison. It's very fast. So we're merely bumping our allocation pointer along, reserving memory for all the objects that we're allocating, and suddenly we're off the end of this region. We do a comparison, oh, it's off the end. That's where the GC comes into play. At this point, we call into the garbage collector and we basically ask for a new allocation buffer. And now here the GC has to make some decisions. It might have some space that it can hand you as a new allocation buffer, but equally, it might need to free up some space before it can do that. And depending on the garbage collector you're using, what it does at that point is different. So if you're using a parallel collector or CMS or G1, that might trigger a stop the world minor collection where the GC tries to free up some space in the minor heap and then can hand you a new allocation region in that freed up space. Or it might be a concurrent collector like ZGC or Shenandoah, which might trigger off a new concurrent collector cycle, or it might stall a bit while it tries to free up some space. So we've looked at the theory. How does it actually map to the code that the JVM generates? So this is a simplified bit of assembly code that is derived from the assembly generated by the parallel collector in Java 8, right? So we've stripped out a few bits like prefetching that they're not entirely relevant here, and but they don't really change much. So the first thing we do is we move the current allocation pointer into a register, and depending on the architecture, might already be cached in one. Then we add the object size, and then we compare it to the end of the allocation region. And if we're over the end, then we call into the GC. Otherwise, we go ahead and we populate the rest of the object, the fields, and we initialize them, and away we go. Now, that's all really nice if we've only got one thing doing allocating. But what happens when we've got lots of threads, as we do on modern computers and modern multi-core processors? What happens when we've got lots of threads that try and do allocation? If they all shared one allocation region, then they'd all be competing to bump this pointer, right? And they would all be competing, and they'd be basically all contending over bumping this pointer, sharing lots of cache coherency traffic, and that would be an absolute performance killer. So instead, how the JVM deals with this is that it uses TLABs, thread local allocation buffers. So each thread has its own allocation buffer to allocate into. And I should stress that those allocation buffers, they're part of the Java heap. So they are just a range in the Java heap. They're not something separate, but they are exclusive to a single thread for the purposes of allocation. Once the thread's done allocating with them, they're just the same as a normal part of the Java heap, right? If the JVM didn't do this, then obviously we'd run into this problem with multi-core scaling. But that means that at any given time, there might be many threads, each independently allocating into their own local allocation buffers, but without having to do any coordination between each other to do that, right? And then they all call into the GC when they need to get a new buffer.
So Sadiq's talked about some of the advances there in terms of JVM engineering over the years, and we've got very efficient modern garbage collectors using pointer bumping techniques and TLABs. And a lot of people take this kind of message and they go, wow, JVM allocation on the JVM is really efficient. So it's basically free, right? We can ignore it. We can just allocate as many objects as we want without any kind of penalty or cost or anything like that. And that's simply not the case. So firstly, in order to understand why that's not the case, we need to take a look at the memory hierarchy within your hardware. Now, the memory hierarchy consists of a series of levels, and the further up the memory hierarchy you are, the faster the memory is. And the lower down the memory hierarchy, the larger the memory is. So we can see that we might have, on a modern CPU, several layers of cache, L1, L2, L3, and also main memory below it. Main memory might be sized in terms of gigabytes. Your L3 cache might be, say, 16 megabytes. These numbers come from a modern AMD Zen 2 processor. And L1 might be 64 kilobytes of cache, for example. But the access times go the other way. So L1 only takes 2 nanoseconds in order to get data into the register in a CPU, whereas main memory may take hundreds of nanoseconds. And similarly with the bandwidth, the rate at which data can be transferred, it's far, far higher at the L1 cache level than it is in main memory. Caches are super, super important for understanding the performance of modern hardware. But there's a problem here, which is sometimes called cache pollution. We're going to talk about it as cache washing. Now, normally, if you hear this expression, you might think of money laundering, the mafia, Tony Soprano, crime. This kind of cache washing isn't a crime as such, but it definitely has negative effects on your application's performance and is still undesirable. So cache pollution. Caches are most effective with a high hit rate. That is to say, the probability that if you request data from them, that the data is there within cache. Lots of object allocation pushes data through caches, evicting old data. Now, modern CPUs use write back rather than write through caches, with the idea of minimizing this effect and minimizing the amount of memory bandwidth overhead that you have. But ultimately, you are still reducing the effectiveness of that cache potentially if you end up in a situation where you are writing data and not immediately reading it. The problem with this is that it causes an increase in your CPU stalls, which reduces the efficiency of your CPU. Now, CPU stalls are where your CPU sits there, it's wanting to decode, fetch, and execute a work, but it's sitting there waiting on data to come into a register from another level of cache, or eventually from main memory in some cases. Stalls are difficult to observe in a production system. They won't show up in a tool like HTOP or VMstat or in a metric system as being low CPU usage. It will look like your CPU is being used, though in actual fact, it's kind of busy working, not really doing anything. It's also worth noting that the garbage collector itself will read different parts of memory from that which your application will do, and it'll have different patterns of access. So there's also a pollution effect on your memory access patterns that comes from running the garbage collector itself. Then there's the plain up cost of allocation in terms of the garbage collector doing its collection work. That's the CPU overhead of a garbage collection. Now, some people will come along and tell you, look, the young generation of GCs of many collectors are copying collectors, and the tenured ones of some are as well. And the result of that is that the work involved in a collection scales with the amount of live objects inside memory, not with the allocation rate. It's a sort of fair point, but even in those situations, increased allocation rates entail more minor collections, and they can also cause other knock-on effects like premature promotion, in which certain objects get bumped up to tenured space, where with a lower allocation rate, they wouldn't be. Some people might say that you get concurrent collectors as well these days, such as ZGC and Shenandoah, and that those collectors are more efficient. They don't have long stop the world pauses, but those collectors still end up doing more work in the background as entailed by higher allocation rates. The next thing to talk about is time to save point. So time to save point is the time it takes for all of your application threads to stop and for us to bootstrap the process of a VM operation. So a VM operation is like a stop the world operation. So it could be, for example, a garbage collection pause. It could be other internal VM operations. In terms of GC, The time to save point entails all these threads periodically polling a bit of memory that's on a certain page. That page is protected by a handler, and when they try and read that bit of memory, it bootstraps into the handler code, and you can use that to get back into the JVM. Now, the problem with time to save point issues is, okay, again, time to save point doesn't directly scale with allocation rates. That tends to be like the number of threads you have is often a cause of increased time to save point. But allocating more, again, causes more collection cycles in practice. And time to save point, even though the time to save point would increase, that save pointing operation will happen more frequently, causing more TTSP and causing more pauses. Time to save point historically wasn't that big an issue in the JVM, but with modern concurrent collectors that don't actually have stop the world pauses that scale with the size of the heap like ZGC and Shenandoah, it's becoming a new bottleneck that you need to be aware of. And then there's the raw cost of actual CPU work that the garbage collector itself has to do, either through background threads or stop the world pauses for collectors that have stop the world pauses on. This is time that could be spent performing work within your application itself, and it's still an inefficiency and an overhead. Yeah.
Great. So we're going to look in a second at why allocation is hard to reason about in modern Java code bases, and why you really need to measure to understand what's happening. So we're going to look at some of these some examples, and there's two main sets of these examples. There is expected allocation, where you expect allocation but actually none happens, and then there's places where we don't expect allocation but some happens anyway. And both can make it quite hard to reason about the actual behavior of your code if you're just looking at it. Right. So the first thing is autoboxing, which shouldn't be confused with beatboxing. So this is where primitives end up needing to be treated as an object, right? So we need to put them into a collection, and generic collections are a great example. So they need to be treated as an object, and so what we actually do is we automatically put them into a heap allocated box, right? And it's relatively easy to end up with unexpected allocation behavior from autoboxing. So this is a good example here. We are taking some ints and we are putting them into an array list, right? But to make matters more confusing, we'll box nearly 900 ints here rather than 1,000, because minus 128 to 127 are actually cached to avoid needing to allocate frequently used short constants, right? And this leads to some hilarious after the fact situations where changing a numerical constant, so suddenly it's more than 127, actually means that now you're allocating boxed integers when you weren't before. And that's something that can throw people out. And if you look at a lot of very high performance Java code bases, they try to avoid allocations. They try to actually use specialized containers for the different data types. You'll see like int array list and long array list and such like that, to avoid this problem specifically. The next thing is strings. So Java strings are immutable. And as Richard pointed out, common source of allocations is actually things like string concatenation, where you might try and build up a logging string or some string to send back to the UI, for example. How the JVM deals with that, actually how the Java compiler deals with that, has changed over the years as well. So if you look at this bit of code here in Java 8 or earlier, the compiler actually transforms this into a string builder, where we actually allocate a string builder on every iteration, and then we append the value of x, we append string.value of I, and then we do toString at the end, which we then assign into x. Java 9, on the other hand, will use invoke dynamic and actually calls a method that takes the strings that need to be concatenated, or actually it can take primitive types as well. It can take types as parameters, and then can concatenate them, but without having to allocate lots of temporary intermediates, right? As a way of decreasing allocation. But the behavior changes depending on what version of Java you're using. The other thing is immutable APIs and factory methods. Now, this is a pretty simple method call here. You maybe expect it to allocate, well, you do expect it to allocate a local date, but Richard has a pretty traumatic experience with it.
Well, yeah, so factory methods can definitely allocate objects. So in this case, you're creating a new local date object for the current time. You might think that would allocate one object just being a local date, but actually it needs to allocate a system clock behind the scenes. It needs to get the current instant out of the system clock. It needs to get an offset out of that clock and then do some calculations before it allocates. So it's not like it's just allocating one object. And we're not saying this to kind of beat down on APIs that allocate lots of objects by design. Immutable APIs, which this is an immutable API, can provide fantastic usability benefits for application developers and can often be a very, very good choice for people to make. It's just a question that you may not be able to just read the code and see exactly where the allocation patterns are just from looking at it.
Yeah, so we've looked at a couple of places. We've got autoboxing, we have strings, there's immutable APIs, and like Richard said, we're not arguing necessarily against using immutable APIs, but we should know that we should know the performance trade-offs we make when we do use things like this. And then, of course, there's the other thing, the other reason for unexpected allocation, that's colleagues. I mean, you have little idea of what might be happening deeper into the code base in calls that you might make into common functions or libraries. And we'll see a few examples of how actually looking at a method in isolation, it's almost impossible to actually work out its allocation behavior. So that's unexpected allocation. Where do we have allocation? Where do we not have allocation where we expect it to happen? Well, this is a vector class. It's got two fields. It's 2D vector. It's got X and a Y. It's got a distance method that calculates the distance to another vector. And we're going to discuss what happens in this particular bit of code here. So this, the JVM has three different, one analysis pass and two different optimizations that combine together to eliminate optimization, to eliminate allocations in many cases. So the two analysis part, the analysis pass is called escape analysis, and what that does is, for an allocation or for an object, it can work out whether that object escapes from its local environment. In this case, from the method that it's allocated in. And if we know that the object can't escape from its method, then we can change the way that we represent it, right? And that's what scalar replacement does. So scalar replacement will take an object and break it apart into its constituent fields, and then actually it will make those fields into effectively local variables, right? So if they're primitives, they'll just get stack allocated, right? Now this should be contrasted with stack allocation. What we're not doing is putting the whole object onto the stack. What we're just doing is breaking apart its fields and then putting those individual fields, treating them like local variables in that method. Now I mentioned two optimization passes. The other one is inlining. So what we saw here is we've seen a.distance b. The distance method is relatively small, so what the JVM has decided to do is inline that. And in inlining it, it now has enough information to be able to say whether A and B escape or not, right? Now, that's worth pointing out because it means that things like things like inlining is based on heuristics. And if, for example, we were to do something in the distance method, let's say we make it longer, or we sample some of the vectors that we're using, or we cache things in some way, we would suddenly defeat the inlining optimization, right? Which means that method would no longer be inline, and that might also mean that the escape analysis can't actually work out whether that object escapes or not. And suddenly we'd have gone from a place where we didn't have any allocation, despite the fact we've got a couple of new keywords here, but we do end up with it later on because some other bit of code in the system has changed.
So Sadiq's given some great examples here of where by looking at the code, it's really hard to understand what's going on. And at this point in time, you might be thinking, look, What on earth is the point in going any further? It's all too complicated. Let's just go down the pub, have a beer, and worry about things less stressful. But I'm here to say, don't worry. It's okay. We can still understand what's going on. We just have to take the right view and the right tooling to understand it. One tool that we can use in order to understand what's going on is an allocation profiler. So profilers tell you what is the source of a resource that's under consumption. And memory profilers tell you, what are the objects that are being allocated. So allocation is the resource that they're telling us about. Here you can see the view from Opsian's web-based continuous memory profiling UI. And we can see that we've got various different types that we're allocating: char arrays, object arrays, and int arrays being the top 3 most common allocation types. And we've zoomed in on the int arrays in order to see where they're being allocated from, because memory profilers are not just there to tell you what's eating all the pies in terms of the type of your system, but they're also here to tell you where in your application code base is the activity going on that's causing the allocation. What do you need to go and fix specifically in order to reduce the allocation rate? Now, there's a couple of different big picture ways that you can implement allocation profilers on the JVM. The first is instrumentation-based allocation profiling. And that is a situation in which you look at allocation sites through some bytecode analysis and add a little bit of bytecode in periodically in order to measure what's going on there. This tends to have very, very, very high overhead when you're allocating objects frequently. So, for example, memory profiling often slows down the overall running of applications by 2 times or 3 times, which is absolutely useless if you want to run it always on in a production environment in the real world with the real data and get to understand what's actually going on there. The other problem of instrumentation-based allocation profiling is it can defeat JVM optimisations. So Sadiq talked earlier about the importance of escape analysis and understanding what's going on the JVM. And if your instrumentation-based allocation profiler takes a reference to that object and hands it off to a method within the profiler, for example, to calculate how big that object is, you've suddenly leaked a reference. It's escaped, and it's broken the escape analysis and defeated scalar replacement optimizations. Another thing that you can have with a problem with instrumentation-based allocation profiling is inlining. If you add more bytecode, too much bytecode to the method, then you will defeat inlining heuristics, and without methods being inlined, you also get a bunch of other optimizations within the JVM made vastly less effective, because the analyses that they rely on don't have a view of as much code to operate on. Sampling allocation profiling. This is another approach, a vastly better approach, to be frank, one that can be applied in production with very, very low overhead, 1% or less. Sampling-based allocation profiling triggers on an event that either could be an allocation or just proportional to allocations, even better. So instead of checking for every single allocation, you look for a time when there's a minor collection or a TLAB refill. This is configurable overhead, so we can take fewer samples if we want to reduce the overhead, or more samples if we want more detail. We can also think about the overhead not just in terms of measuring the objects itself, but also in terms of collecting the stack traces. Maybe you want to collect a sample from every TLAB refill, but maybe only 1 in 100 of those result in a stack trace that you collect, because stack traces are another thing that has overhead in terms of the collection. So sampling allocation profiling can be vastly, vastly lower overhead. And you shouldn't worry about the sampling having less accuracy than an instrumentation-based approach, because at the end of the day, what you're really interested in is knowing, as I say, who ate all the pies. What are the biggest consumers of your allocation rate, not the actual raw numbers. As long as you're doing this accurately in proportion to allocation rates, you're still good. You should be a bit worried still. Some poorly designed JVM TI agent configurations can disable JVM optimizations. For example, reading the names of local variables can disable escape analysis. But if an agent is efficiently and carefully designed, it can still work with very low overhead.
Great. So we are now going to go live, right? So we're going to look at some examples here, and then we're going to go and actually have a look at what the allocation behavior is. Right. So this is our first example. Looks pretty basic. The core is this remove duplicates method here, right? What it does is it takes the first element from the past list and then removes it, and then it removes all duplicates off that from the list as well, right? Simple stuff. Richard, what do you think the allocation behavior for this method is going to be? Just putting you on the spot here.
I think you're a cheeky man, Sadiq, and you're trying to trick me here. So we've got our first local variable that you've unboxed by putting it into an int local variable. And then when we use it, we pass it to the equals method of these boxed integers. And that's going to cause it to be reboxed, to be passed through there. So I think, you've already talked about autoboxing. I think this is an autoboxing related problem. That's my guess.
Okay, that's pretty reasonable. That's pretty much along the lines of what I would have assumed. So now we're going to go actually have a look at what it actually does, right? So we've wrapped this method in a program. What we do is we create a list, and that list has a bunch of increasing integers. And then we keep calling this method until the list is empty, essentially. And then we do that whole thing in a loop. And we're going to use Opsian's continuous allocation profiling functionality here. And we're going to go and have a look at what the actual allocation behavior of the program is, right? So bear with me for a second. Right, let's get out of here. And we are going to go and have a look. So this is, we're going to do an allocation report. Now, what did we say that we thought it was going to be integers, and the highest, so the biggest source of allocations, 91% of our allocations and also bytes allocated are long arrays. So what's kind of going on here, right?
All right, I admit it, you fooled me.
So I mean, but these are integer arrays, right? So I mean, if it was an int array, maybe, but I don't. So let's have a look and see. So long arrays, and we've got this in remove duplicates. We've got remove if, and then there's this end bits thing. So let's go into our IDE, and let's actually have a look at this code, right? So here's the code that we've got. It's the same code that was up on our slide before. It's this remove duplicates. Yeah, we'll go into our IDE, and trusty IntelliJ will click remove if. And we've got this method here, remove if. Run this predicate over the iterator, runs a test, and then just removes elements if they match. But this isn't allocating any long arrays. So kind of what's
But Sadiq, this is a default method on the collection interface.
Yeah.
Could it be the case that the default method is being overridden by an implementation within the collection itself?
Yeah, so let's go and have a look at this array list remove if here, right? So array list, let's go to array list, and here we go. So we've got array list remove if. Now this is a much more complex implementation than the one that we saw on the collection interface, right? And that's because it supports some functionality. It makes some guarantees that the collection, the default implementation of the collection doesn't. And what it actually does to satisfy those guarantees is it actually runs the predicate over all the elements, and then it actually keeps a bit set of the positions in the array list that need to be removed. And then after it's finished running the predicate over everything, then it goes through and it removes all the elements that need to be removed, right? And it's got this rather morbidly named death row long array here, which is allocated by this n bits that we see here. And that is actually allocated when we call remove if. Now, it's worth pointing out that the method itself takes a list. It doesn't necessarily take an array list, right? And if we'd passed in a linked list, we would have got the default implementation, which doesn't have the same allocation performance. It doesn't allocate long arrays. So you would do no allocation, and that's so what it's being called with changes how it performs. But also what's happened here is that the allocation behavior of this actually changed from Java 8 to Java 14. In Java 8, actually we allocated Java 8 actually allocated a bit set regardless of whether there was actually any elements that need to be removed. Whereas in Java 14, it's got this very neat optimization here where it actually checks that there is actually anything that matches this predicate. And only when it finds something that actually matches the predicate does it then actually construct this bit set from that point onwards. So as a neat property, that if you're not removing anything, you don't do any allocation, right? Now, it might seem like a contrived example, but the reason we picked this is actually it's something that we've hit in a production code base, a very high performance production code base that was a source of excess allocations on a critical path, right? One that we didn't expect, and that from manual code inspection didn't seem to be the case, and that we only were able to find when we actually did some measurement, right? Now, the next thing we're going to do is we are going to look at, assuming I can find the slides, we're going to look at the next example, which is the next example, which is allocation in a bit of a bigger code base. So this is looking at a system, right? And to show you that it's a bit more complex when we're looking at a larger system, right? So in the UK, property transaction data is publicly available. You can just go and download months and years worth of what house was exchanged and how much it was. And we've essentially taken taken all that data, and this system is basically a cache and an HTTP front end that sits in front of it, right? And again, this is an example we've constructed, but it's really similar to the kinds of things we've seen when we're doing performance optimization on real systems. So I set it running a little while ago on my desktop, which has got pretty warm by now, and we're going to look at some of its behavior in Opsian systems and JVM diagnostics dashboards. I'm running a constant workload against this, so we're firing a fixed number of requests per second at this system. And we're going to go and have a look and see what actually it's doing. So we will go over here and let us go and look at what the system is currently doing. So the system is, this is the JVM and systems diagnostics dashboard. It has a lot of information on it, and we're only going to be using a small amount of that information. So the idea is that there's pretty much everything you need in here to diagnose what's actually happening in a system. But we're going to just look at the application pause time. So application pause time is the percentage of time that the application has spent pause compared to the time the application was actually doing productive work, right? Now, obviously, you want that ratio to be quite low, because if it's very high, then, well, you're not doing productive work. And that's hopefully why you're running the applications to do productive work. If you're just there to burn CPU, well, you could just set fire to stuff, it'd be easier. And so what we can see on this graph here is that about 75% of the time, we get these peaks where about 75% of the time we're spending nearly all of our time just sat in GC, right? This is a system that's not very happy, essentially. So let's go and have a look at what's going on. We can go and have a very quick look at the collections themselves. So these show you that we're doing loads of scavenge collections here we're running the parallel. This is running the parallel GC. Lots of scavenge collections. Each one of these points is basically one or more collections, and we can see the time spent there in these collections. But what we're really interested in is actually what are we doing in terms of allocations. So we can go and have a look at this allocation rate. So allocation rate is the number of bytes that we're allocating per second. Right, so this system has got a spike in allocation. So every so often, every about 4 to 5 minutes, it's got a spike of allocation behavior that then just kind of trails off, which is weird because we're running it on a constant load. So what we can do through Opsian is we can highlight this area, and then we can say, right, show me what we were actually doing back then in terms of allocation. So what we can see here is that we're actually doing we're actually spending nearly all our time allocating char arrays, right? We can click and we can see where this is happening. So we can see that we are doing it. It seems like it's to do with CSV parsing, and it is happening inside sales data, read sales, sales data, get sales data, and then the sales query search just down here, right? So let's grab our IDE, and we would jump into performance problems. So let's go to sales query. So sales query search. This is basically where it starts. We can see here that we are we're essentially taking this query string and we're running through this in-memory cached sales data, and we are looking to see whether it matches, the query string matches country, postcode, district, any there's lots of string fields in this data. So basically whether it matches any of these string fields. And then we return it but we do it inside a Guava query, a Guava cache, right? Now, what is going on here? So if we see we're doing, if we go and we look at this report again, we can see that actually this is all happening in get sales data, read sales. So let's go through and click get sales data. And now let's look at the get sales data itself called read sales. And we can see here that this is doing some CSV parsing. Now, what's happening in get sales data? And we can see here actually our IDE is flagging up something here. This is not being used. And what we're seeing here, so what we do is we check sales data for whether it's null. If it's null, then we basically return a new set of sales data. But if not, we return the cached one. And what we're actually failing to do here is we're failing to actually populate this cached in-memory sales data, right? Now, interestingly, this is the kind of behavior that we're only seeing because this example actually has periodically it invalidates its cache. So what it does is that it expires its cache. Potentially you've got a new bit of data coming in and we want to expire the cache. So it actually expires the whole cache in one go. And because of that, you then see this flood of allocation in that we are then repassing all these things. If we didn't expire the whole cache in one go, if we only expired individual elements at a time, all we would see for this system is we just see that it was using a constant high amount of CPU and a constant high amount of allocation. We wouldn't have actually seen that there was an issue unless we'd actually measured it.
Cool. So I think we've seen from this that only looking at the code in and of itself is a bit of a waste of time. It's like Sisyphus pushing a boulder up a hill. It's a heroic but ultimately pointless task. Sisyphus was an idiot. Pretty sure that's the moral of that story anyway. So the idea that you can just read code and understand its memory allocation pattern in the presence of things like JIT compiler optimisations, libraries doing all sorts of things you may not understand under the hood, different cost models for different garbage collectors, different JVM versions, it is as useful as pushing a rock up a hill. You really need to measure what your production system is actually doing. And memory profiles are a great tool to have in your belt for achieving this goal, especially ones that run with very, very low overhead in a production environment. It's like a measuring tape for object allocation. Easy to use, easy to find low-hanging fruit, and often a source of great optimization opportunities. So Sadiq and I work at Opsian. We're a performance tooling and consulting company. And if you're interested in having a further discussion with us about any of the topics you've raised in this talk, come and have a chat with us afterwards. We're on Twitter. We're also in the chat. And Opsian itself as a product is something that some of our customers have described as a magnifying glass for our service. Anyone who is on the chat now, we are happy to take questions about the talk. Thank you very much.
Thank you, Richard and Sadiq, for your talk. And everyone can give you a round of applause, a virtual applause in the chat if you want. And we have one question in the chat. Jack would like to know, do pointer bumping and T-labs apply to all 12 open JDK garbage collectors, or do some use different mechanisms?
As far as I could find, I couldn't find anything that wasn't using the T-lab path. You can turn it off and you can get some horrendous performance problems if you do turn it off, so don't do that. But as far as I couldn't find anything that wasn't using pointer bumping in T-labs, basically. For the common case, there is a separate case that doesn't use pointer bumping for large allocations.
Okay, I hope that answers Jack's question. And it seems there are no other questions, so I hope everyone enjoyed the talk. And thank you again to you, Richard and Sadiq, for being here.
Thank you for coming.
Thanks.